Okay, so good afternoon, everyone. So this is the tutorial for week 2. So you can download the problem set on the Moodle tutorial week 2. So we start with question 1. Okay. So what is the binary form of 193 and what is the binary form of 0.1? So let me share with you the piece of paper. So you see, I mean, there's a very simple algorithm. So let we do it bit by bit, so step by step. So 193. Okay, so this is in base 10, yeah? And you want to expand it into a binary form. So we draw a table. So X, and this one is you take the remainder of X when you divide it by 2. So you put in 193 here. So when you divide it by 2, the remainder is 1, right? Because it's an odd number. And so you got 96, and you divide it by 2, the remainder is 0. And then you divide it by 2, you got 48, remainder is 0. You got 24, divided by 2, remainder is 0. And then you divide it by 2, you got 12, remainder is 0. 6, remainder is 0. 3, okay, remainder is 1, okay? And now when you divide it by 2, well, it's 1.5, but actually, you take away the fractional part, so it's a 1, yeah? So 1, when you divide by 2, then you have nothing left, and you have a remainder is 1. So you have to stop the algorithm here. And now you have to read the digits from the right. Okay, so now if I read the digit from the right, then I have 193. So I got 1, 1 here, 1, 1, and then 0, 0, 0, 0, 0, 5 times. 1, 2, 3, 4, 5, and then 1. Okay, so this is my binary representation. So I have to check whether my calculation is correct. So remember, so this one you can represent as a powers of 2. So this is power 0, yeah? And so this one is power of 2, right? Okay, so this one power 0, power 1, power 2, power 3, power 4, power 5, power 6, power 7. Okay, so question? No audio for you, okay? So maybe I have to say a bit louder. Is it? Okay, that's fine, yeah? So, okay, so now if I put my calculation here, you see, so the power is 7, right? So it's number 1 here, right? So this one means that corresponding to the 7 plus 2 to the 6, yeah? And then because all of them are 0, so I don't have to worry. So I just have the very last one is 2 to the 0. Okay?
That is weird.
So then this one will be 128 plus 1. And you can sum it up. So this one is just 193. Okay. And so now that is the binary representation of 193. So about 0.1. So 0.1. See, the problem with 0.1 is now you cannot apply the previous algorithm. Previous algorithm, you divide it by 2, right? And 0.1, you cannot divide it by 2. So the algorithm for number less than 1 is you have to multiply, okay? So now the algorithm is you have y, and you have to multiply by 2, yeah? And you check whether 2y greater or equal 1 or not. Okay, so now y is 0.1. Yeah, and then you multiply by 2, so you got 0.2. Sorry, 0.2, and 0.2 is not bigger than 1, so you put in 0. Okay, and then you multiply by 2, so you got 0.2 here. And now you check. Okay, so now 0.2, is it greater than 0.2? You multiply by 2. Is it greater than or equal 1? Well, so you got 0.4, so 0.4 is still less than 1. You put in 0 here. Okay, and now you do the same. So now 0.2, you multiply by 2, so you got 0.4. So 0.4, you check this condition. So 2 times 0.4 is 0.8. So 0.8 is still less than 1, so you put 0 here. Okay, and now you multiply by 2, so you got 0.8. Okay, now something happened here. So 0.8, when you multiply by 2, okay, then it's greater or equal 1. Well, it's greater than 1, right? Because 1.6. You'll write 1 here. So now 1.6 is beyond 1. So you have to modulo 1. So you take off 1, so it's 0.6 here. Okay. And now 0.6, then you check, okay, so 0.6 when you multiply by 2 plus 1.2 greater than 1. So put in 1 here. Okay, and then now, you multiply by 2, take away 1, so you got 0.2. So 0.2, you multiply by 2, you got 0.4. So only 0 and 0.4 and 0 and so on. Now you see the pattern. So the pattern is, it just keep repeating, right? So you see that actually, I mean, you can do this one forever because 0.1, 0.2, 0.4, 0.8, 0.6, 0.2, 0.4, 0.8, 0.6, 0.2 again and again. Okay, so this one will goes on forever. And then, because it's like it's like 1/3 when you try to approximate by a decimal. You got so you got 0.33333, yeah, infinite sequence. So the same here. So this one is 0.1 when you try to write down in terms of decimal. Sorry, when you write out in terms of binary, then you got a infinite sequence. So you read from the left here. So you got 0 and then 0, 0, 0. So 3 0 here, and then 1 1, then 0 0, then 1 1, then 0 0 again and again. So it's infinite sequence. Okay, so that is the binary expansion of 0.1. Yeah. So now the next question is, how do you convert back from binary to, so any question so far? So in the solution, I will explain how I get this algorithm. Okay, so this algorithm can be explained, but I put it in the solution because it takes a lot of time trying to explain it. Yeah, then you can read the solution and you can see why we can get these algorithms. And now, suppose now we go in the other way. So now, suppose I have a number. Suppose I have a number, then I want to write down in terms of decimal. So this one is my binary number. Okay. So now remember the power. So the power of 2, right? So the power is, so after the dot will be -1, -2, -3. Yeah. So after the dot and before the dot, so power 0, power 1, power 2, power 3, power 4. Right, for each digit. So then this one will equal 2 to the 4. So we have 0, 0 here. So you got 2 to the 1. Yeah. plus 2 to the 0. Okay, so we ignore the zeros here because you multiply by 0. And now after 0, so this one you have 0 here. So you have 1 over 2 to the 2 plus 1 over 2 to the 3. Okay, because the power is negative 3. Yeah. And now you sum it up. So this one is 16 plus 2 plus 1 and plus quarter and 1/8. Yeah. And this one is just equal 19.375. Okay, so you can check. Okay, so any question? Good. No more question. No question. Then I move on to the next question. Yeah. So the next question is about real min and real max. So how do we explain real min and real max? So question 2, explain how we get the real min and real max. So remember the diagram for the floating point number system. Yeah. So you got a plus or minus for the very first bit. And after that, you got 11 bits for the exponent. Yeah. So this one, 1 bit for the sign. Yeah. And then this one, you got the fractional part is 52 bits. Yeah. Well, because the total has to be 64 bits. So you got 64 bits for floating point numbers. And then a floating point number is, well, a normalized floating point number is something like this. So 1, right? So the first digit has to be 1. And then you have digit number 1, digit number 2, up to digit 52. Time 2 to the exponent. Okay, so exponent will be between E min and E max. Yeah. And if you remember IEEE standard, then E max is just 1023. Yeah. So this one is the maximal value of exponent, right? Because remember, you know, you have 11 bits, yeah? So 11 bits is of exponent. So it means that you can have up to 2048 possibilities, okay? But because you reserve some values, well, first you want a negative power as well. And then you reserve some special values for not a number, infinity, not normalized number. So eventually you just have E min is only minus 1022 and E max is 1023. So this one is IEEE double precision. Okay. Yeah. So now real max. So real max, so the consequence is real max will equal, you know, you turn on the bits to 1, right? So 1, 1, 1, 1, 1, 1, 1, 1 to the very end, okay? Times 2 to the E max. Yeah. And then, so what is the expansion in terms of binary? Sorry, in terms of decimal. Well, so this one is just 1 plus 1/2 plus 1 over 2 square plus dot 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 dot. So what is the last term? 1 over 2 to the something here. To the E max. So E max is right here, yeah. So what is the last power? What is the last power here?
52.
See my pen? You see my pen? The tip of my pen, yeah. So what number I should write down here? 52. Yes, it's correct because we have 52 digits. Yeah. Remember, we have the 1 up to 52. So the first digit is 1/2, and the last digit is 1 over 52. Yeah. And now, what is this? So this one just a geometric sequence. Yeah. So what does it equal to? So anyone remember the formula? That will be anyone remember the formula? So what is the formula for the geometric sequence? Yes. So well, not quite. I think okay. So very close. But you see now let me remind you the formula. So 1 plus alpha square plus dot alpha n. Okay, will equal 1 minus alpha to the power n plus 1 over 1 minus alpha. Okay, so in our case, alpha is 1/2. Yeah, so we have 1 minus 1/2 to the power of 53 divided by 1 minus 1/2. Okay, so it matches 1023 here. Yeah, so this one is just the formula for the geometric series. Yeah. So then what you have is, so 1 minus 1/2 is 1/2. You flip it, so you got number 2, right? And then here you have 1 minus 2 to the minus 53. Yeah. So you're very close. Yeah, but it should be like this. Okay. And then this one will be 2 minus 2 to the minus 52. Yeah, because 2 here, then you minus, so become plus 1. Yeah, so times 2 to 1023. Okay, so this number is not easy to compute, so I have to put into MATLAB. Okay, so if I put into MATLAB, then, so let me share with you my MATLAB. So you see my MATLAB, yes. So now if I put in 2 minus 2 to the minus 52 multiplied by 2 to the power of 1023. And I got this number. And you type in real max. See, you got the same number. So this is the maximal floating points numbers you can store in 64 bits floating point numbers. Okay, it's the maximal number you can get. Yeah, and it's true for other language as well. I mean, if you use C or Python, if you use 64 bits, then the maximal value of a floating point number is still this value. Okay, so now what happened to real mean? So what is the minimal value? So now what is real mean? So now real mean, so remember, I mean, this definition of the floating point number, so real mean is now I just set all the digits to be 0 and the exponent to be in mean. Yeah, so real mean will be, so real mean will be 1.000. Okay, so everything is binary here, times 2 to the e mean. And this number just equal 1. Yeah, so then this one is just 2 to the minus 1022. Okay, so now what happened if I put in MATLAB 2 to the minus 1022? So if I put in MATLAB 2 times 1000, sorry, minus 1022, then I got this number. So what is real mean? Okay, so real mean is exactly this number. Well, you can ask why real mean is not equal 0. Well, what is the answer? Why 0 is not a minimal real number? I mean, in terms of positive numbers. So why real mean is this tiny, tiny number? Why it's not equal 0? Anyone? Type in the chat box. Why real mean is this number? Why real mean is not equal 0? Anyone? Yes, because it normalized, you know, because the first bit is 1, yeah. And if the first bit is 0, then you just have 0, and then, you know, like the exponent field has a reserve value. So when you put exponent equals 0, fractional part equals 0, then you get 0, plus or minus 0, okay? But because you see the normalized form at least give you extra bit to store, you know, more values. And then a non-normalized, you can store it as well. And then in that case, then the exponent has to set a different value, okay? Okay, so now we move on to the next question. So the next question will be a script like this. So now let me share with you the script. So if you see, maybe you haven't seen it yet, but you will see. So let me clear this screen, yeah. And then where is the script? So the script will be right here. So you see the script, yeah. So now the script look like this. So if you see the script, look like this. So you set n and you set m, n equals 6, m equals 2, and then k is integers. So this one just means that k is integers of 16 bits. Okay, so you take the fraction n over m, but this one, this special command just say that k is integer, 16 bits, so instead of 64 bits, yeah. And then you set a matrix equal a 0 matrix of the size n times n. Okay, and now what does the loop do? Well, maybe it's a bit like more instructive. Try to understand what is a for loop do, right? So now let me show you my analysis of this piece of code from line 5 to line number 9. So now suppose I share you my paper. So I assume that you have the program with you, yeah. So now let me share the piece of paper. We want to understand the program before we run it, okay? So now suppose I have So I assume that you just look at the program, yeah? So now I just want to run it, at least by hand. Okay, so you see M is equal to, right? So you have a loop I, and I run from 1 to M. So you have I equal 1 or M or I equal 2, right? And then inside the loop, then you set the value low and high. Yeah. So now the very first step, when I equal 1, then low is just equal what? Well, low equal I minus 1 times K plus 1. Yeah. So I minus 1, I equal, yeah, so it equal 1. Yeah. And then what is high? High will equal 1 times K. And what is K? K is N over M. Okay. Yeah, but K in our case, yes, it is just equal 3. Yeah. So high just equal 3. And now you run to the next line. So now you say that, okay, so A low to high. So will be A1 to 3, comma 1, colon 3, yeah, equal I is just equal 1, yeah. So once, and remember K is just equal 3. So you got 3 here, okay. Yes, it's integers N over M, but in our case, it's equal to 3. I just want to make it concrete. Okay, I want you to see what is going on here. So then the matrix A will look like this. Yeah, from 1 to 3. So row 1 to row 3, column 1 to column 3. You set it equal 1. Yeah, so just a block 3 by 3. Okay. And the matrix A look like this. So what happened to other entries? So what are the values of other entries? What are the values of other entries of the matrix A? So this is the, the block set by this command, yeah. 0, yes, because, remember before the loops, we set A equals 0, right? Set 0 everywhere. So it will be 0 everywhere here. Okay. And then now you go down, to the end. Then now you have to repeat the loops. Yeah. So now I will equal 2. So I will equal 2. Yeah. And now what is the value of low? So now what is the value of low and what is the value of high? Uh, 4, yes, correct. Because, now it will be K plus 1, so 3, yeah, 4 and 6, yes, correct. And now you see now the command will be A4 to 6, comma 4 to 6, equal I times 1 K, comma K. So I is 1, sorry, I is 2, right? So 2 times 1, 3, 3, yeah? And now the matrix A will be something like this. So 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay, and now from row 4 to row 6, now you set it equal to, so row 4 is here, 4, sorry, row 4 is here, 4, 5, 6, yeah? In column 4, 5, 6, so you got. So this is the result you got from running the script, okay? So now we run it and see whether our prediction is correct, okay? So I share my MATLAB again. And now if I let it run, so I have to type in the command from blocks, yeah? So I save as block. So you see the matrix A is exactly what you predicted, yeah? So this one is the first blocks, okay? And this is second blocks, okay? And now the last command It's just number of non-zeros elements. So when you write out n and z, this one just means the number of non-zeros element. And you can see that, you have 9 entries here and another 9 entries here. So totally 18 entries, 18 non-zero entries. Okay. So now the next part of the question is, now we know the logic of the program. Yeah, we change it. We change n to 10,000 and m equal 10. So now suppose I change n to 10,000 and m equal 10. Then the question is, how much memory in terms of gigabytes, yeah, I need to store the matrix A. So now forget about this example. Forget about this case when m equal 2, right? So now you have m equal 10. Okay, and n equal 10,000. Okay, so 10 to the 4, yeah. Then now what is the size of the matrix A? So first, like how many entries does the matrix A have? So how many entries? No, not 10,000. I mean, the number of entries should be more than 10,000. Yes, 10,000 square, yeah. So it should be 10,000 square. So it should be n square, right? And then one entries, yeah, takes 8 bytes, yeah, to store. Remember, 64 digits, 64 bits equal 8 bytes, yeah. 1 byte is 8 bits, yeah. 64 binary digits equal 8 bytes, yeah. So then the memory, so the number of bytes to store A is just an square, yeah, right? Because one entry is 8, take 8 bytes, yeah. So n square entries take that many bytes, yeah. So will be 8, 10 to the minus 4 raised to the power 2, so 8 to the 8. Okay. And now remember the question asked you to use gigabytes. So now 1 gigabyte is 2 to the 30 bytes, yeah. So there's other conventions say that 1 gigabyte is 1 billion bytes, yeah. But now, I mean, I just use this convention. So other may say that 1 gigabyte is 1 billion bytes, yeah. So this one is other convention or other definition, yeah. So it's up to you. You can, if you use this definition, then the number of gigabytes to store A will be that many divided by 2 to the 30. Yeah, so 8 times 10 to the 8 divided by 2 to the 30. And if you put in the calculators, then you got about 0.75 gigabytes. Okay, so maybe GB. Yeah. Now the next question is a bit more complicated. So the next question say that, okay, I want to save memory, so I don't want to store all the entries of the matrix A. I want to store only the non-zero entries. Okay, then how much memory does it take? So So now the next question is, how much memory does it take to store only the non-zero entries as a sparse matrix? Well, first we have to find out what is the number of non-zero entries. Of A. Okay, so in order to do that, maybe it's better to go back to the simple case, yeah? Remember, this is the case we had before, yeah? So how many non-zero entries in this case? So in the small case, yeah? So how many non-zero entries? 18, right, remember? But that 18, yeah, so the formula, so it is just the number of blocks, yeah? So the non-zero entries here, it's just the number of blocks times k square, right? K square is the size of each block, yeah? Right? So now in terms of m and n, so what is the number of blocks? So remember, in terms of m and n, what is the number of blocks? How do you get 2 blocks here? Why do we get 2 blocks? In terms of m and n, anyone? So how many blocks you have? M blocks, yes, correct, yes. And what is k? Well, k is just equal n over m, right? Okay, so you see, so this is the general formula, right? The number of blocks multiplied by k squared. Okay, so now if I use this formula and I go back to this case, then I just have m, well, I just said that equal the number of blocks times k squared again, yeah? And the number of blocks is just equal m, and k squared is just n over m squared, right? And m is 10, yeah? And n is 10 to the 4th, and m is 10 so square, right? Well, then you just have the number of non-zero entries. So then you have, so this one is 10 times, so this one is 1,000 squares, so 10 to the 6. So just 10 to the power 7, okay? And then the number of bytes, okay? So the number of bytes to store non-zero entries is just equal 8 times 10 to the 7, right? And then the number of gigabytes, well, here we set up to store non-zero entries. It's just 8 times 10 to the 7 divided by 2 to the 30. Okay, so this one is it's just a simple calculation, yeah? So then this one gives you around, you put in the calculator around 0.0725 gigabytes, okay? So any more question? So you figure out the number of non-zero entries, and each entry takes up 8 bytes, yeah? So this one 8 bytes per entries, yeah? Non-zero entries. Okay. and then you get out the number of gigabytes. Yeah. So any question so far? So far, so good. Okay, so everything is okay, right? Okay, so now the next question is epsilon of n. So this one is related to the floating point system as well. So you have epsilon of n. Okay, it's just the gap between n and the next machine number after n. So the gap between n and the next machine number after n. Okay, so maybe we do some example. So now suppose I got 2. Okay, so what is epsilon of 2? Well, so now we do it step by step, yeah? So we expand 2 in terms of a binary, in terms of a floating point number system. So you got 1.0000. So in binary times 2 to the 1. Yeah, so this is the normalized form floating point system, floating point representation of number 2. Okay, so now how many digits here? How many digits do I have here? How many binary digits? How many digits do I have from the first 0 to the last? Yes, 52 digits, yeah. So remember, we're still in floating point system, double precision, yeah. So 52 digits. So then 2 plus epsilon 2 is, I mean, think of your car odometers. Now you just turn on the last digits, yeah. So then 0, dot, 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 and then the last one become 1, okay. In the middle, all of them are zeros, and multiply by 2 to the 1. So then epsilon of 2 is just 0.0000. The last digit is 1, okay. And you remember this one is just 2 to the minus 52. So there's nothing in the front, right? Multiply by 2 to the 1. So this one gives you 2 to the minus 51. Okay. And it's always 52 for double precision. So remember, so double precision is 64 bits. So this is the pictures. So for double precision, okay, for IEEE, so this is the pictures, yeah. For IEEE, for 64 bits double precision, and this is always 52 bits. Okay, for single precision, it's a different number, but we don't use single precision in MATLAB. Okay, and then there is quadruple precision, which is 128 bits, but we don't use it either. So in MATLAB, we just use 64 bits number. So then always to have only 52 digits. Okay. So now you got epsilon of 2 is 2 to the minus 51. Okay. So now I show you that in MATLAB, when you put in epsilon of 2, so epsilon of 2, okay, and then 2 to the minus 51. You see they're the same, okay? And you see epsilon 2 plus 2 will be definitely bigger than 2. Yeah? No. It's normalized. It just means that the very first digit is 1. Yeah, but then the number, remember inside the computer, they store only the fractional part of the significand, yeah? And it's for 64 bits, floating point numbers, then they store only 52 digits of the significance. Yeah. Okay. And now, so epsilon of 2, yeah, is if you divide it by 2, right? You plus 2, then it's no longer bigger than 2. You see, so epsilon 2 is the smallest. You have to increase in order to get to 2. And you see, if you take epsilon plus 2, then it's not bigger than 2 as well. Yeah? Remember, epsilon without parameters is just epsilon of 1. Okay, so this one is just the same as epsilon of 1. Okay, so maybe one more example. Yeah, so one more example. What is epsilon of 3 and epsilon of 4? So maybe one more. So what is epsilon of 3 and what is epsilon of 4? So you do the same. So now suppose I have epsilon of, so what is epsilon of 3? Yeah. Well, first you have to expand 3 in terms of binary. Yeah. And then you put in normalized form. Then this is how you get number 3. Okay. And then 3 plus epsilon of 3, you just turn on the very last digits into 1. Okay. And then this one gives you epsilon 3 is 0.000, the very last digit is 1 multiplied by 1. So then this one is the same as 2 to the minus 52 multiplied by 2, so 2 to the minus 51. Okay, so maybe do one more. So what happened if I got 4? So 4, then this one becomes 1.00 up to the n, but now multiply by 2 to the power 2. Okay, so remember 4, then it will be 1 times 2 to the power 2. So then 4 plus epsilon 4 will be, you turn on the last digits to 1. Then you got 2 to the 2 here. Then epsilon 4 is just equal to the minus 52 multiplied by 2 to the 2, right? What is 2 to the minus 50? Okay. So how do you define epsilon of any number? Well, first you have to expand it into a floating point number in a normalized form. Then you get out the power. Okay. And once you get out the power, then you just take epsilon of 1, where is 2 to the minus 52, multiply with 2 to that power, and you got epsilon. Yeah. So you can check that. So now, let me share the MATLAB with you. Yeah. So epsilon of 4 is this number. And remember, we say our computed value is 2 to the minus 50. Okay, so they're the same. Okay. So you get the idea, right? Okay, so now we have time to do one more question. So number 5. So this one, number 5, related to the lab yesterday. So remember, we have catastrophic cancellation. If you have two numbers very close, two real numbers very close to each other, right? And now suppose in the case of solving a quadratic equation, then you have minus b plus square root b square minus 4ac over 2a, yeah? Well, and x2 equals something. We just forget about x2 for the moment, yeah? And now you can see that when b is positive, yeah, and b squared minus 4ac is very close to b. Yeah, I mean, I write this means that it's very close to b. Then catastrophic cancellation can occur. Yeah. So remember when you take the difference between two real numbers very close to each other, yeah, then the relative errors can close up. So how do we fix it? Okay, so one way to fix it is to use different formulas. So now, suppose I take x1 equal minus b plus square root b squared minus 4ac divided by 2a, and I multiply by the conjugate of this expression, yeah. Well, I multiply, but then I divide it, so it's the same, yeah. Okay, and now if you remember the formula for a minus b, a plus b, yeah. So then this one will be, okay, so now maybe we should put a plus instead of a minus minus. So maybe a plus is better. Okay. Then the top will be equal b squared minus 4ac minus b squared. Okay. And the bottom is just b plus square root b squared minus 4ac times 2a. Yeah. And then now the b squared got cancelled. So you got minus 4ac divided by 2a and b plus square root of the discriminant. And the 2a got cancelled as well. So you got only minus 2c divided by b plus square root b squared minus 4ac. And you can see the last formula is equivalent to x1, but there's no catastrophic cancellation. Yeah, no catastrophic cancellation. So you can see that so epsilon only increase when we reach a new power of 2. Yes, exactly, yes. So when you reach to the new power, yes, this is a correct observation. When you move to the next power, then epsilon of that number, yeah, is, so, you know, when you write epsilon, it means that epsilon of 1, okay, when you have no input parameters. But when you write epsilon of n, then it's the gap between n and the next machine number. Okay, so now the next question is, how do I tell the results that there is no catastrophic cancellation? Well, because you see, now this one is just a plus of two real numbers. So remember here, I assume that b is positive. So this one is just a plus of two positive numbers. So here there is, so catastrophic cancellation is when you have a minus of two real numbers that are close to each other. Good point. What happens if you have a minus in the square root? Very good point. So remember this one, you can deal with it separately, because when b squared is close to minus 4ac, then you have a double roots. Remember? So you can check it separately. Yeah. So because when the discriminant equals 0, you have a double roots. So that is what you're asking, right? The minus in the discriminant, yeah. So you can check it separately, but that is the best we can do. At least, you know, you can see that is the best we can do in this case. Okay. So any more questions? So any more questions? Otherwise, I stop the recording first and